Okay, in this lecture we're going to start our section 3.4 material on partial fractions, or sometimes called the method of partial fractions. Now, this method of partial fractions is going to be another technique or method for integrating functions. And before we see how this technique works, I've been saying I want to stress how we know when we're supposed to use a particular technique. So for this new technique of integration that we're going to talk about, partial fractions, when is it used? And I mentioned here that it will be used to integrate rational functions. So here, partial fractions is used to integrate rational functions. So those are functions of the form r of x, which is equal to p of x over q of x, where p and q are polynomials where the degree of p, that is the degree of the numerator, is less than the degree of q, the denominator. Now we'll consider at the end of this section some examples of rational functions where the degree of the numerator is greater than or equal to the denominator and see how to handle that. But to start our discussion, we'll consider this case where the degree of the numerator is less than the denominator first. And the general idea of this method of partial fractions is to take a single rational function that might be a little bit complicated, and we're going to try to decompose this rational function, r of x, into the sum of smaller, more manageable pieces, which we refer to as partial fractions. And the way that we go about decomposing this rational function into the sum of partial fractions depends on what form our denominator, q of x, looks like. So there are altogether 4 cases which we will consider. And the first case which we will discuss is called the case of distinct linear factors. So let's suppose that the denominator, q of x, of our rational function is the product of distinct linear factors. So as an example, suppose that we have a rational function that looks something like what we're given here, where our denominator can be factored into the product of linear factors. So those are factors of the form ax plus b, where all 3 of these factors are distinct. That is, none of them is a repeated factor. There is no like x plus 1 squared or x plus 3 squared, but all of these factors only appear once. So for this type of rational function, we could decompose this into something of the form a over x plus 1, where x plus 1 was the first factor in our denominator, plus b over x plus 2, where x plus 2 was the second factor in that denominator, plus c over x plus 3, where x plus 3 was that third factor in our denominator. Now, if we had other distinct linear factors, let's say there was like an x minus 7 term, then we would have an additional term in our sum, something of the form d over x minus 7, where these numerators, the constants or the values a, b, and c, are some constant values. And the question is, well, what are these constants, a, b, and c, that would make these 2 functions equal to one another? Because if I can rewrite my single rational function as the sum of these smaller parts, well, I know how to integrate each one of those parts individually. But looking at this original function, well, it wouldn't be obvious how to integrate that function in the way that it's written. So to illustrate this technique in this first case of distinct linear factors, let's look at the following example. So we are asked to evaluate the antiderivative of x minus 1 over x squared plus x, which is a rational function. It is the quotient of two polynomials, where the degree of the numerator is less than the denominator. Here our numerator is a first degree polynomial. The denominator is second degree. So anytime that we're integrating rational functions, we should probably try the method of partial fractions that we're going to discuss in this section. And our first step in this method of partial fractions is to see what the factors of our denominator are. So we want to take our rational function and factor the denominator as far as possible. So in this example, I see that from the denominator, I could factor out an x, and I would be left with x plus 1. My numerator is x minus 1, and then we had our dx term on the end. So my denominator is the product of two distinct linear factors, x and x plus 1. So I claim that I could rewrite this integrand, that is x minus 1 over x times x plus 1, as the following decomposition, something of the form a over x plus b over x plus 1. So for each of the factors that I had in my denominator, I'm going to have some constant term divided by that linear factor when I write out my decomposition. And the question is, well, what are the values of a and b that would make these two functions equal to one another? So to find them, I'm going to take both sides of this equation and multiply by this common denominator. That is x times x plus 1. And that will leave me with a left-hand side of x plus 1, which would be equal to a times x plus 1. But then when I divide by x, I would just have the x plus 1 term. And then I would have a b times x plus 1. But when I divide by the x plus 1 term, I have just b times x. So now I want to try to solve for a and b. And there's a couple of ways that we can go about doing this. I'll illustrate in this case of linear factors an approach that's a little bit quicker, but doesn't work later when we talk about the case of quadratic factors. So let me introduce this simpler way to solve for our coefficients here. So let's suppose that I was trying to solve for my coefficient a. Well, I might ask myself, what would be a value of x that I could substitute into this equation to get rid of this b coefficient? And I see, since we're multiplying b by x, if I were to choose x as 0, I would only have an equation involving a left over. So let's try taking a value of x as equal to 0. So if x is equal to 0, then the equation which we just had would reduce to negative 1 is equal to 1 times a plus 0. So right away I have the value of a must be negative 1. And similarly, if I wanted to solve for the coefficient b, I ask myself, well, what value of x could I substitute into this equation to kill off the a term? And since a was being multiplied by x plus 1, if I take x to be negative 1, then that would get rid of the a term. So if x were negative 1, the equation would be negative 2 is equal to negative b, which implies that b would be 2. So once I have the values for a and b that I was looking for, let me go back to the integral that we're interested in. So this integral of the function x minus 1 over x squared plus x dx can be rewritten as the integral of a over x, where a was -1, plus b over x plus 1, where b was +2. So we're taking this decomposition that we found, substituting in the specific values for a and b, and rewriting our integrand as a sum of these smaller partial fractions. And for each of these terms, I know how to find my antiderivative. The antiderivative of -1 over x would be the negative natural log of absolute value x. And then plus, I've got 2 times the antiderivative of 1 over x plus 1 would be the natural log of absolute value x plus 1. And since this was a indefinite integral, I'm going to include an arbitrary constant c to get the most general antiderivative. So I've got the following. So this first example illustrates how the method of partial fractions will work in general. So the idea is to take a single rational function and rewrite it as a sum of smaller partial fractions, which we can handle individually. And we see here an example of how we would go about finding that partial fraction decomposition of our function. If we know what general form it has, we can solve for the constants a and b algebraically. And once I have those constants, then I can integrate my partial fraction decomposition term by term. Now, one thing that I want to take a look at in this first example, before we move on, is an alternative way that we could have solved for our constants a and b. And I want to illustrate this because it will be useful when we start talking about the case of quadratic factors. So before I move on, let me back up just a bit and look at another way that I could have solved for the constants a and b in this problem. So here, another approach which I could have used, and this will be an approach which is necessary later in this section, would be to expand the expression that I have on the right-hand side of this earlier equation. So if I expand, I would have ax plus a plus bx, and then collecting like terms, well, I could group the ax and bx terms together, and I would have a plus b times x plus a. And now, in order for this equation to hold, the two functions on the left and right-hand sides of this equation must be the same. So that is, the coefficient that I have for x on the right-hand side, a plus b, must be the same as the coefficient for x on this left-hand side. So on the left-hand side, we had 1x. So I know that a plus b has to equal 1, and the constant coefficients must also match. That is, a has to equal the constant coefficient on the left-hand side, which was -1. So I find that a is -1, and if a plus b has to equal 1, that means b is 1 minus a, or 2. So we get the same decomposition that we had when we used our other approach. So the function that we started with can be rewritten in the form -1 over x plus 2 over x plus 1 dx. And as we did earlier, we can evaluate the antiderivative term by term. We've got the negative natural log of absolute value x plus twice the natural log of the absolute value of x plus 1 plus c. So in this first example, I wanted to illustrate those two different approaches for solving for our constants. And the main reason that I want to illustrate this second approach is that it will be necessary when we consider some more complicated examples later in this section. So let's look at another example, get a little more practice with this approach. So in our next problem, we're asked to evaluate the integral of this rational function, where the degree of our numerator is less than that of the denominator. So that immediately should suggest a partial fraction decomposition. And our first step in doing a partial fraction decomposition is to factor our denominator as far as we can in order to see what our factors of the denominator look like. So for this denominator, I see that I could factor out an x, and I would be left with x squared minus 1. But then that x squared minus 1 quadratic can be factored as the product of x plus 1 and x minus 1. So by factoring my denominator as far as possible, I see that it consists of 3 distinct linear factors: x, x plus 1, and x minus 1. So in this case of distinct linear factors, we can rewrite our function as a partial fraction decomposition of the form a over x plus b over x plus 1 plus c over x minus 1. So for each factor that appeared in our denominator, we have a term in our decomposition, which is some constant divided by that linear factor. And from here, I need to find the values of a, b, and c that will make these two functions equal one another. So to do that, I could multiply both sides of this equation by this common denominator, x times x plus 1 times x minus 1. And I'm left with x squared plus x minus 1 is equal to a times, I would be left with x plus 1, x minus 1, plus b times x times x minus 1 would be my remaining factors, and then plus c times x plus 1. So this is what I would have when I multiply the previous line through by the common denominator. So let's see if we can go about solving for our coefficients. Now in this case of linear factors, I can solve by trying to find specific values of x to kill off certain terms. So proceeding with that approach here, if I were to try to solve for a, I would ask myself for the terms involving b and c, what value of x could I substitute in to kill off those terms? I see they're both being multiplied by a factor of x, so if I chose x as 0, I would be left with something only involving a. So let me say the following. If x is 0, then this equation reduces to -1 is equal to a times 1 times -1, so negative a, which implies that a would be 1. Now, if I want to solve for b, let me ask myself for the terms involving a and c, what value of x I could substitute in to kill off those terms. I see that both of those terms involve an x plus 1. So if I chose x to be -1, then I would be left with something only in terms of b. So if x is -1, the left-hand side of our equation reduces to -1. That would then be equal to b times -1 times -2, or positive 2b, which implies that b would be -1/2. And for my last coefficient, c, that I'm trying to solve for, I ask myself for the terms involving a and b, what could I substitute in for x to kill off those terms? And here, both of those terms involve a factor of x minus 1. So if I choose x equal to positive 1, those terms will disappear. And my equation would be given by 1 is equal to 2c, which implies that c would be 1/2. So once I have the values for a, b, and c, I can rewrite my integrand as this partial fraction decomposition, and let's see what we have. So we're now looking at the integral of a over x, where a was equal to 1, plus b, which was -1/2 over x plus 1. So I might write that as b times 1 over x plus 1. And then plus c, which was 1/2 over x minus 1. So I might write that as 1/2 times 1 over x minus 1 dx. And now each of these smaller pieces I know how to integrate. For 1 over x, we would have an antiderivative of log x. Then we have a minus 1/2, the natural log of absolute value x plus 1, plus 1/2 times the natural log of absolute value x minus 1. And at this stage, since we had an indefinite integral, I can include my constant of integration plus c. All right. So these first two examples illustrating the case of distinct linear factors for our denominator. Now the next case that we'll talk about is case 2, or the case of repeated linear factors. So let's suppose that the denominator of our rational function, q of x, is the product of repeated linear factors. So as an example, let's say we had something like this, a rational function where our denominator could be factored as x plus 1 cubed times x plus 2. So here, my first of these linear factors, which was x plus 1, appears 3 times. We've got 3 factors of x plus 1 since it was being raised to the 3rd power. So in this case that our denominator involves some linear factor which is repeated, our partial fraction decomposition will take the following form. So here we would have something of the form a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. So I'm going to have as many factors in the decomposition as powers of that linear factor that appear in my denominator. So in this example, since I had x plus 1 to the 3rd, I'm going to have a term involving x plus 1 to the 1st, x plus 1 squared, and x plus 1 cubed for my denominators in this decomposition. If we had something like x plus 1 to the fifth, I would have to include 2 more factors in my partial fraction decomposition. Now, the last term that we have in our denominator is a distinct linear factor, x plus 2, which only appears once. So we would also need to include some constant d over that x plus 2 term. And we've only got one factor there since that term only appeared once. So let's look at an example of this method of partial fractions, illustrating the case of repeated linear factors. So in this next example, we're asked to evaluate the following integral. And as soon as we see that it involves a rational function where the degree of the numerator is less than the denominator, that should immediately make us think of this method of partial fractions. And our first step in the method of partial fractions is to factor the denominator. We need to know which case we're working with, case 1 or case 2. So for this function, we see that we can factor out an x squared from the denominator, and we would be left with the factor of x plus 2 dx. And that's as far as this can be factored. So when I look at this denominator, I see, well, there are 2 repeated factors of x and 1 distinct linear factor of x plus 2. So in this case, we could decompose our function into a partial fraction decomposition of the form a over x plus b over x squared, since we had a repeated factor of x, and then plus c over that last linear factor x plus 2. And again, the question is, well, what are the values of a, b, and c that will make these two functions equal to one another? So to find them, I'm going to first simplify this equation by multiplying both sides by this common denominator, x squared times x plus 2. And this would give me an equation, 5x squared plus 3x minus 2 is equal to a times x plus 2 plus b times x plus 2 plus c times x squared. All right. So now, let's see if we can solve for our constants a, b, and c. So using the same sort of approach that we had considered previously, let's see if we can choose certain values of x that would allow me to solve for each of my coefficients, a, b, or c. So when I'm trying to solve for a, for instance, I would look at the terms involving b and c and ask myself, well, is there some value of x that I could plug in that would kill off both those b and c terms? And I see that there is not in this case. There's no common factor for the terms involving both b and c. So we start to see already in the case of repeated linear factors that approach of substituting in values for x to solve for your coefficients is not always the easiest approach. So instead, let's talk about the other approach, which I mentioned, to solve for our constants a, b, and c, which requires us to expand our function on the right-hand side of this equation. So if I multiply this out, I would have ax squared plus 2ax plus bx plus 2b plus cx squared. And if I group like terms together, I would have a plus c times x squared plus 2a plus b, all times x, plus 2b. Now, to solve for my coefficients, I know in order for this equation to hold, if I copy down my left-hand side of this equation again, I know that these functions on the left and right-hand side of this equation must be the same. So the coefficients must agree for each term. That is, the coefficient of x squared, which was 5 on the left-hand side, must equal a plus c, the coefficient for x squared on my right-hand side. The coefficient for x on the left-hand side must equal the coefficient for x on the right-hand side. And the coefficient, which is my constant on the left-hand side, must equal the constant coefficient on the right-hand side. So copying these conditions down, we have a plus c has to equal 5. 2a plus b has to equal 3. And 2b has to equal -2. So looking at our third equation here, we find immediately that b would be -1. And once I have b, I could substitute that into the second equation and solve for a. So if b is -1, I would have 2a is equal to 3 minus b, or 4, and it follows that a is 2. And once I have a, I could substitute into the first equation, and I would have 2 plus c is 5, so c would have to be 3. So once I have these coefficients for a, b, and c, let's look at the integral that we started with, but writing our integrand in this decomposed form. So our decomposition was a over x, we found a was 2, plus b, which was -1, over x squared, and then plus c, which we found to be 3, over x plus 2, dx. So by rewriting our function in this decomposed form, I can now integrate directly, and I would have twice the natural log of absolute value x, plus 1 over x for the antiderivative of 1 over x squared, then plus 3 times the natural log of the absolute value x plus 2, plus c. Since this was an indefinite integral, I don't want to forget my constant of integration. So this example illustrating how this second case of partial fraction decomposition works if we have some linear factor which is repeated. So let's look at another one. In this next example, we're asked to evaluate the integral of x squared over x minus 3 times x plus 2 quantity squared. So here we have the integral of a rational function. It's a quotient of two polynomials where the degree of the numerator is 2. We had x squared. And then the degree of the denominator, if we were to expand this, well, we have x to the first and then some x terms squared. So we would have a lead coefficient of x cubed. So the degree of the denominator is less than the numerator. And this suggests that we could try a partial fraction decomposition. Now our denominator is already factored as far as we can. And we see that our denominator is the product of a distinct linear factor, x minus 3, and a repeated linear factor, x plus 2 squared. So in this case, we would try to decompose our function x squared over x minus 3 times x plus 2 squared in the form a over x minus 3 plus b over x plus 2 plus c over x plus 2 squared. So since that x plus 2 factor was repeated, we had two factors, we will have two terms involving x plus 2 and x plus 2 squared in our decomposition. So again, in order to solve for a, b, and c, I will first multiply both sides of this equation through by our common denominator. And I'm left with x squared is equal to a times x plus 2 quantity squared plus b times x minus 3 times x plus 2 to the first plus c times x minus 3 to the first power. So, as we did in our last example, in order to solve for a, b, and c, let's try expanding this expression on our right-hand side. So expanding, I would have a times x squared plus 4x plus 4 plus b times x squared minus x minus 6 plus cx minus 3c. And if I distribute the constants a and b, I would have an a x squared plus 4ax plus 4a plus bx squared minus bx minus 6b plus cx minus 3c. Or grouping like terms together, I would have an a plus b x squared. So for my x squared terms, we just had the a and b term. For my terms involving x, we had a 4ax minus bx plus cx. So grouping those, I would have a 4a minus b plus c all times x. And then grouping my constant terms, I have a 4a minus 6b minus 3c. And this has to equal x squared. So we arrive at the following. Equating these coefficients, our 1x squared on the left-hand side must equal a plus b x squared. So a plus b has to be 1. Now equating the x coefficients on the left and right-hand sides, well, on the right-hand side, we had 4a minus b plus c, but we did not have any x coefficient on the right-hand side. So this 4a minus b plus c must equal 0 so that we don't have any x term. And similarly, our constant coefficient that we're left with, 4a minus 6b minus 3c, must equal 0 since there was no constant on the left-hand side of our equation. So from here, we've got a few approaches that we could use to solve for a, b, and c. So one approach that we could make use of is the following. We have, from our first equation, a is equal to 1 minus b. So if I take that expression for a and I substitute into my other two equations, I would have 4 times a, which was 1 minus b plus c is 0. So this reduces to 4 minus 5b plus c is 0. Or 4 is equal to 5b minus c. Now substituting that expression for a into my third equation, I have 4 times a, which is 1 minus b, minus 6b minus 3c is 0. And this reduces to 4 minus 10b minus 3c is 0. Or equivalently, 4 is equal to 10b plus 3c. So looking at my last two equations here, they now only involve b and c. So let's see what we would have if we solve for one of my variables in terms of the other, or perhaps a little easier to do here, would be something like the following. So we would have our first equation, 5b minus c is 4. And our second equation, or well, technically third equation here, was 10b plus c is equal to 4, plus 3 times c is equal to 4. So in order to solve, well, I could take my first equation, multiply through by 3, so that my coefficient of c is a negative 3c. And if I add that to the equation below it, then the c terms cancel. So I would have 15b plus 10b, or 25b, is equal to 12 plus 4, or 16. So b would be 16 over 25. Now once I have b, I could substitute b back into one of my previous equations to solve for c. So maybe using the second equation, I have c is equal to 5b minus 4. Now 5 times b would be 16 over 5 minus 4. So 16/5 minus 4, which would be 20/5, would leave me a negative 4/5. And I know that a was equal to 1 minus b. So 1 minus 16 over 25 would leave me with 9 over 25. So once I have a, b, and c, I can look at my integral again, but in its decomposed form. And I would have a, which was 9 over 25 over x plus 3, or over x minus 3, excuse me, plus b, which we found to be 16 over 25, times 1 over x plus 2, plus c, which was negative 4/5, with our 1 over x plus 2 squared, dx. And we can now integrate term by term, which would give us a 9 over 25 natural log of absolute value x minus 3, plus 16 over 25 natural log of the absolute value of x plus 2, and then I would have a plus 4/5 times 1 over x plus 2 to the first power, plus c. So this last term that I was integrating, I'm actually using a u substitution where u is equal to x plus 2. So we're left with something of the form 1 over u squared, which has an antiderivative of negative 1 over u. So times that negative 4/5 gives me my positive 4/5, 1 over u, which was my x plus 2 term there.